Hey guys, it's your boy Chili. Welcome back to Hardware 3D. Today, we're going to be loading and rendering materials for our model. Now, I'm often guilty of doing what is called burying the lead in these videos. I only show you the highlight at the very end, the final product. So let me give you a little appetizer here. Let me show you what we're working towards today. So this is our familiar nanosuit model, but you may not recognize him because he's gotten a little sexier over the past few commits. As you can see, we've got textures now, we've got diffuse textures, and we have a specular map on this bad boy. And you gotta admit, it looks pretty goddamn sexy. He's on fleek, as the kids like to say. So, how did we get to this glorious point? Well, to figure that out, as you do, you look at the Git history. So we start here, rename the nano model. I renamed our old model to nano hierarchy because it's a hierarchical model. And our new model is not hierarchical. But what it does have is it has a material. And that will give, information about all the different meshes, what they look like, what kind of textures they have. What it also has is images for textures. Very important. And we'll look at these a little more later on. Now, what you might be noticing in this commit is, well, Chili, where is the freaking OBJ file? Well, let me tell you, fool me once, shame on you. You're fooled, you can't get fooled again, is what I'm trying to say. So I got screwed again, and the reason why was because while I had excluded OBJ files in the models directory, I had not excluded OBJ files in subdirectories of the models directory. So I had to splice that into here, and everything is good now. But anyways, moving on, let's look at the first code change. It's a little weird, it's a little interesting. But the place where we want to actually load the material data for right now is in parse mesh, because the material data is being applied to the mesh, and it is defined per mesh. So what we're going to do is, instead of just taking the graphics and a reference to the mesh, we also need an array of Assimp material objects. But we want to take them in, like these guys here, like the reference to the AI mesh, we want to take that in as a const. The only thing is that a pointer to an array of pointers is a pointer to a pointer. And because that the first pointer there is inside of the AI scene, it is going to be const. So what that means is what we're passing in here is essentially a non-const pointer to a const pointer to an array of const AI material. And that's why you got to have the const here and the const here. It's a little freaky. It might take a little while to get used to, but when you're working with double pointers and const, you got to know what you're doing to a certain degree. So that's what that is. And then when we parse our meshes, we're also going to pass in the M materials array of materials that exists in the AI scene. And down here against the parameter there we added. And here I'm just showing you how you actually get access to the material for the current mesh. The mesh has a member, which is an index into the array of materials. You use that index to access the materials, and that will give you your reference. Dereference it, you get a reference to the material that is indicated for the current mesh. So far, so good. Now, the next thing I did here, this code doesn't do anything useful. All it does is it loops through the properties of the material, and it gets a reference to them. And then what I use this for is I could look then in the debugger, see what kind of properties exist on the material. So see, I set a breakpoint here. If I run this in the debugger, and I look for prop, here is the property. So we got one property here, the name, the key name of the property is !mat.name. Now the data down here is, the way they do this is they use some weird funky kind of polymorphism that they rolled their own instead of, using the polymorphism that's built into the C++ language. So, I'm going to shame them, I'm going to king shame them a little bit, but at the end of the day, they did give us a cool library to use, so, But anyways, we can't really look at the data that much, but we can look at the names of the different properties that we have here. And if we see we got the shading mode, ambient color, diffuse color, specular color, emissive, shininess of the material, opacity of the material, transparent color, refractive, texture file, texture UV, W, another texture file. So lots of different bullshits in here. Great. How do we get that texture information out of there? Well, it turns out it's not that hard. Let's take a look at this commit here. We'll scroll down. We deleted that stuff because it wasn't doing anything. So here, first thing we do is we're doing a little check here. Because not every mesh is required to have a material assigned to it. So if a mesh doesn't have a material assigned to it, it's going to have a negative index. So we want to check for that first, because we don't want to be indexing into this array with a negative index. It's not going to end well for us. So we do that check here. We get the reference to the material that is for this mesh. And we create an AI string object. That's rolled their own string object. And then we call get texture on the material to get a texture. Now they have different, I don't know what this is, probably like a constant or an enumeration, but there's a texture type you specify, and then you specify the index. So we want the first diffuse texture, indexed at 0, and you give it a pointer to this string here, and it will fill it with the file name. And then once we have the file name for that texture, we can load the image. And I'm just hard coding this stuff in here for right now. It'll be better later on, trust me. But it's going to be in models, nano textured, and then the file name of the texture here. And we create a texture bindable from that surface that we've loaded. And we also create a sampler because we need a texture sampler. And then you're good to go. Except, of course, if you run this, you should probably understand that you're not going to see the texture. Because first of all, we haven't done anything with our shader to use that texture information. And second of all, we haven't loaded the texture coordinates into our geometry. So the next step is to actually load the texture coordinate. We're going to add the texture coordinate to our layout. Because remember, we have our dynamic vertex layout here. Right now, we're defining it that it contains a 3D position and a normal. And to that, we're going to add a 2D texture channel. Now, pop quiz, what do you think will happen when we run this code? If we're in debug mode, we're going to get a very nice assertion failed here. Param count does not match number of vertex elements. And you can see it takes us to our dumb template code, which isn't that helpful. But if we go up the call stack a little bit here into parse mesh, we see the problem. Oh yeah. So yeah, we defined that it has these 3 channels, but we're only loading 2 channels in here, and that's probably not a good idea. Assertion saves the day. In our next commit here, you can see we're loading texture coordinates from mesh data. It's pretty straightforward. We just add this line in here, which is going to load m texture coordinates 0i into an xmfloat2. Now, you might be wondering, why are there 2 subscripts in here? That's because, well, if you look at the member m texture chords, you will see that it is an array of 8 AI vector 3D. So, as you can see, there are 8 channels for texture coordinates, and we want the first channel, channel 0. And the I here, of course, is to select the texture coordinate in channel 0 that corresponds to vertex I. Now, if we actually run this, you will see, of course, no textures. Why? Well, I mean, we've loaded the texture, we have the sampler, we have the coordinates, we have all this actors set up, but we're not actually utilizing them because we haven't modified our shader yet. So for the change to our shaders, well, first of all, in mesh.cpp, we're removing, in our material constant, we're removing the color because we don't need a constant color anymore, since we're going to be loading that color from our diffuse texture. In the vertex shader, it is pretty straightforward. We add the texture coordinate in the output, in the input, and here we just assign it. Not really anything amazing going on there. In the pixel shader, it's pretty much the same. We remove the material color from the constant buffer. We have to add in declarations for our texture and our sampler. We take in a 2D texture coordinate in here, and down in here, what we're doing is we're replacing this material color with the color that is sampled from our texture. And if you load that up, here is what you get. We've got our boy, and he is all textured up. Beautiful. Looking pretty good. Not quite as shiny as in the final product. Doesn't look very shiny at all, actually, but he is textured. Now, at this point, it would behoove us to take a look at what kind of maps we're dealing with here. Now, there's three kinds of maps that come along with this model. One is the diffuse map, and we're already loading those and rendering them. Another one is the normal map. That is going to be a topic for a separate video sometime in the near future. But the third kind of map here is the specular map, and that is what we are going to be tackling at the second half of this video. So what the specular map does is it tells you how much specular reflection you will get off of a given pixel or texel, independent of its diffuse color. Now, if we open one of these bad boys up, what you're going to see is you're going to see it actually has, it has color, but it also has an alpha channel. And it's so we can infer that some information is being stored in the RGB, and some information is being stored in the alpha. And we also know that for specular, we have two components, right? We have the exponent, and then we have the actual intensity, which can be a 3-channel color value. So obviously the RGB is going to map to the intensity, and then the alpha would logically map to the power, or the shininess, or the glossiness, if you will. And there are different ways of doing specular maps. Sometimes it's just an RGB with no alpha, and the shininess is just a constant that is part of the material. Sometimes it's not RGB, it's just a single grayscale value, and that might actually, it might be in a grayscale texture of its own, or it might be in a different texture. Like, for example, in the, what is it called? The normal map, you have the RGB, and those map to X, Y, Z, and then the fourth alpha channel can actually contain the specular intensity. So there's many ways of doing it. But this way is probably one of the more advanced ways of doing it, I guess you could say. More flexible, more powerful. Now, the first step of utilizing this is obviously we have to load these textures. This means that our system has to be able to do something it hasn't been doing yet, which is load multiple textures for a single drawable. So to our texture, we've added a slot data, so we can have multiple texture slots, and you define that when you create the bindable. So now in the bind function, instead of just hard coding it to slot 0, we now use the actual slot. And in mesh.cpp, what we're going to do here, after we load our diffuse texture here, we are then going to call getTexture with AI texture type specular, and we're going to load that bad boy as well. And we're going to load that one to slot 1. As you can see here, we're defaulting to slot 0, and that's very nice because that means all of our previous usages of texture won't break. They will have the same slot 0 that they always had. Now that works if all of your materials happen to have both kinds of textures, but in our scene, in our model that we're loading right now, we can notice that the glass has a normal map, has a diffuse map, but it lacks a specular map, which makes sense because the visor, it's just a single material, it's just glass. So the specular reflection is going to be constant. You don't need to have a texture for that. So we should probably check the return value of getTexture. If it is AI return success, then we create a bindable for that. But otherwise, that means that that texture, or that specular map doesn't exist, so don't try to create a bindable for it. So the next thing what I do is I duplicate my pixel shader here. I just copy and pasted the pixel shader, and then I'm going to modify my duplicated pixel shader. But let me see, what did I do in mesh.cpp here? Okay, so I've got a little flag, bool, has specular map, and if we succeed in loading the specular, then we set that to true. And then down here, what we're doing is if we have a specular map, then we are going to load the Phong specular map shader. But if we don't have a specular map, we're going to load the Phong shader that does not use a specular map. Makes perfect sense, hopefully. Down here, I just twerked the material parameters a little bit. And then in our Specular Map shader down here, what we're doing is we are sampling from the Specular Map. And then we're splitting that into a 3-channel color intensity, which is a specular map.rgb. And then we're also sampling that into a specular power, and that's just the alpha channel. And then our specular component here, we're saying that that is the attenuation times the specular color intensity times the power of the specular boy, raised to the specular power. All that good stuff. And that is what we've decided to do with our lives. Now you can tell by the name of this commit that that probably wasn't a very good life decision. But let's see. Let's see how she rolls. So here we are with our Specular Map technology. And as you can see, doesn't seem to be working properly. We're not getting the shininess. I'm not feeling the shine. But we got a weird highlighting, but it's a very diffuse, broad highlight. It doesn't look anything like a specular map that you're used to, but we can see a little bit of specular on here. It looks like. It's weird, but it looks like it exists. So the question is, what the hell is going on? Well, let me go back to this here and let me just show you I can identify, 2 real separate issues. One of the issues is the visor. We can see specular sort of happening on our visor, but not in the middle. And that doesn't make any sense. It's glass. We should have specular, but yet we don't have any specular. Why is that? Well, if we look at the shader, we can see right away what the problem is. So the shader we're using is the Phong Vertex Shader, the Phong Pixel Shader without the Specular Map. And we can see here is that we take the diffuse, the ambient, and the specular, and we multiply them all by the texture, the diffuse texture. But if the diffuse texture happens to be black, which as you can see here, it is black in the middle of the visor, that's all that color is going to get multiplied by 0, and you're not going to see anything. So in fact, we don't want to multiply our diffuse texture times all of these components here. We want to multiply the diffuse texture times the diffuse light. And we want to multiply the specular texture against the specular light. Or if we don't have a specular texture, then we want to multiply the constant specular value against that. So the specular intensity should actually be coming in here. And if we look at the next commit, fix spec on Helmut, we can see, I bring my texture sample, and I multiply that by the diffuse and the ambient. And I add the specular to that at the end. And the specular has had its specular intensity multiplied up here. So now those are nice and separate. And if we run that bad boy, we can see right away, this is looking a lot better. It's not killing the black here in the middle of the diffuse texture isn't killing our specular reflection. Now we only have our second problem here, which is this weird kind of spotlight highlight that's huge and fat and dumb on our texture. Why is it so huge and fat? Well, we know that the power of the specular power, or the shininess, controls how big and how diffuse the highlights are. So when the power is very low, we have a very kind of blurry, dull highlight, like what we're seeing here. So this would indicate that our power is way too low. And then we look at our shader and we ask ourselves, well, the power is coming out of this alpha channel. Well, what is the range of alpha? It's going to be from 0 to 1. Well, what is our normal range of powers? Powers generally range from 0 to like maybe a few hundred. So obviously, we can't directly use the alpha as our power. We need to have some kind of mapping between alpha and power. One very simple mapping would be a linear mapping, basically scaling the alpha up by 100 or so. So if we look at the next commit here, we can see, I create a little static constant here, specular power factor of 100, and then when I load it out of the alpha channel, I multiply by the specular power factor. I give myself a linear mapping there. I also took the specular color intensity, I pulled it out of here, and I put it into here. So now it's just because here's what we're sampling the color for the diffuse. Here's the sampled color for the specular. I don't know. I like it better this way. It doesn't really matter. But what does matter is that we actually do a proper mapping of alpha to specular power. And I mean, if we do that, now you can see, okay, this is starting to look, this is more like it. This is what we kind of expect and desire. Now we've got proper diffuse highlights on this bad boy. He's looking shiny. He's looking happy. Shiny, happy people. Now, I did a linear mapping there, but that's not the only mapping that you can conceive of. And I actually did a little research online, and I saw a Stack Overflow thing that indicated that for OpenGL, it's more common to do an exponential glossiness mapping. So what it is the alpha value is the exponent. You scale the exponent by 13, and you take 2 to that power. So it's 2 to the power of your alpha scaled by something. And so I figured, well, if that's common, might as well try it out. And it looks good because that's what you see in the end product. So I decided to go with it, but I don't really know. And the mapping that is used is up to the person who creates the actual asset. So you have to have your asset, or you have to have your mappings and your assets, they have to match up. I don't know what the original intended mapping is. So basically all I have to do is pick something and see if it looks good. But I decided to go with this since it seems to be maybe more common. I don't know. Obviously doing different mapping functions instead of linear using exponential here, or you could also use quadratic, will allow you to tweak the dynamic range at different parts of the power scale or whatever you want. But anyways, here is another kind of mapping, and it seems to work well, at least for this model. For those of you interested, by the way, here is the actual Stack Overflow question and answer where I got it from. So if you want to look that up yourself, you can type this in, or you can do a Google search with the words and you'll find the thing and you can read the stuff. Now, when we have our specular map, we use that. But when we don't have a specular map, we're just going to use a constant glossiness. And instead of hard coding that glossiness, it would be nice if we could specify it in the material file. Now, if we open up the material file in the text editor, we can see it's just plain text, and you can understand a lot about the file format just by looking at it. Here's the name of the material. This is the body material. This is the glass material. This is the ambient color of the material. This is the diffuse color. This is the specular color. Here are the textures for the diffuse, for the normal map, and for the specular. And here is the constant shininess, basically the exponent for each of these materials. So this is what we want to load in the absence of a specular map. So how do we do that? Well, if we look at this command here, we can see, first of all, I just set a default shininess of 35. And here, if we fail to load the specular map, we call material.get AI mat key shininess. And this, I'm going to go over this a little bit in a second. This is really dumb, but this macro here will control what material parameter that we get. And this is passed by reference, which is weird because sometimes they pass out parameters by pointer. Other times they use reference. It's all over the place. But anyways, this will load the shininess into there if it exists. And then down here in the bottom, we are not going to be setting the specular power to just a default of 40. We leave that uninitialized. And then after creating the structure, we set the specular power equal to the shininess. Seems pretty straightforward, but there is some weird thing. This function, material.get. So if we inspect it with the power of our IntelliSense, we're going to see that it is a function that takes 1, 2, 3, 4 parameters, none of which are optional. And yet we're passing it 2 parameters. So this obviously looks like it's not correct. And you know what? But if you look at the documentation for Assimp, you're going to see, if we can find it here, material get. Yeah, they pass it one of these macros and they pass it the parameter and it loads it into that parameter. So you might be thinking at this point, what the heck? And you might look at this and you might say, well, this documentation is dated 2012. Maybe it's out of date. But if you try it anyways and you load it, you run it, you compile it, it works. So then, just out of curiosity, you mouse over this macro and you see that the macro is actually 3 values separated by commas. So this expands into 3 arguments. And this is the 4th argument, and that's why it works. And it's at this point that I just have to shake my head. I just have to say, wow. Just wow. But there you have it. That's how it works. You've got this this macro, and if you want to know the macros to get any of the other parameters, you can just look at this material system page. They've got all the macros listed in here. But yeah, here it is. And it's awesome. It's sexy. It works great. That's gonna about do it for this video. In the next video, we are going to do just a little teensy bit of architectural tweaking because our system has changed quite a bit with the introduction of, loading models with Assimp. There's stuff in here that doesn't make sense anymore in the bindable drawable system, and we're gonna do a little bit of an improvement. We're not gonna go on a whole detour of several videos or anything, but we're gonna have one video. We're gonna make some improvements. We're gonna make it nicer. Not perfect, but better. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.